understanding algorithm efficiency through practical lens. In an age where milliseconds can determine success or failure, algorithm efficiency stands as a cornerstone of modern computing. From search engines racing against time to deliver results to complex AI models processing petabytes of data daily, understanding how algorithms perform under pressure is not merely academic, it's survival. This exploration delves beyond abstract theory by connecting performance metrics with real-world implications. We'll examine why even small improvements matter when scaled across billions of operations, revealing hidden costs lurking behind seemingly innocuous code choices. The cost of inefficient algorithms. At first glance, inefficiency might seem trivial, just a minor delay here or there. But consider a web service handling 10 million requests per second. Even a nanosecond difference per operation accumulates rapidly into measurable delays that impact user experience and infrastructure costs. Such inefficiencies often manifest in unexpected ways. A poorly optimized sorting routine could become a bottleneck during peak traffic hours, while unnecessary memory allocations may trigger garbage collection pauses that disrupt streaming services requiring uninterrupted delivery. Bottlenecks, critical junctures where processing speed becomes constrained despite adequate hardware resources. Dominance analysis, identifying which parts of your algorithm contribute most significantly to runtime complexity. Space-time trade-offs, choosing between using extra memory for faster access versus maintaining minimal footprint at potential expense of execution speed. Let's take a concrete example from social media platforms that process vast amounts of user interactions each day. When implementing recommendation systems, developers must carefully balance between accuracy requirements and computational demands. An inefficient approach might analyze every possible connection rather than employing graph traversal techniques limited to relevant subsets. Evaluating time complexity fundamentals. Time complexity analysis provides us with mathematical tools to predict scalability without running actual tests. Big O notation offers a standardized way to describe growth rates regardless of implementation specifics or hardware variations. Consider three basic scenarios: constant time operations unaffected by input size, linear time processes proportional to dataset dimensions, and exponential time methods doubling in duration with each additional element added to inputs. A simple lookup in an array demonstrates constant time complexity, O(1), since accessing any position requires equal effort irrespective of array length. In contrast, scanning through elements to find a target value represents linear time complexity, O(n), increasing proportionally with number of items processed. Big O notation deep dive. While many developers understand the general concept of Big O, few grasp its nuances fully. It describes upper bounds on worst-case scenarios but doesn't account for average cases or best-case optimizations sometimes implemented in practice. To illustrate this distinction, imagine searching for an item within sorted list arrays. Binary search typically operates at O log n time complexity due to having search space iteratively until reaching desired result. However, if target happens to be located near beginning of array, actual runtimes would dramatically differ from theoretical predictions. It's crucial to differentiate between asymptotic behavior and practical realities. For datasets smaller than certain thresholds, which vary depending upon architecture characteristics, lower-order terms may dominate over leading coefficients identified through formal analysis. Misinterpreting these relationships leads to common pitfalls. Some engineers mistakenly believe their system will scale indefinitely because they've achieved O(n log n) complexity, even though underlying constants could make such implementations less efficient than simpler O(n superscript 2). Alternatives operating on manageable-sized inputs. Spatial considerations beyond just time memory consumption forms another critical dimension affecting overall efficiency. While optimizing CPU cycles remains essential, failing to manage memory usage introduces separate challenges impacting both performance and reliability. Caching strategies provide one solution, but require careful balancing act. Too much caching risks consuming excessive RAM, potentially forcing swap file utilization that degrades system responsiveness. On other hand, insufficient cache mechanisms increase disk I/O overhead, which itself becomes expensive in high-throughput environments. Garbage collection introduces further complications. Languages relying heavily on automatic memory management introduce unpredictable pauses when reclaiming unused objects. These interruptions interfere especially with applications demanding low-latency guarantees like online gaming servers or financial trading platforms. Tips for measuring real performance gains. Gaining true insight requires moving beyond theoretical analysis towards empirical validation. Benchmarking frameworks allow comparing different approaches objectively before committing to production use. Select representative test cases covering typical workload patterns instead of synthetic benchmarks that fail to reflect realistic conditions. Measure end-to-end latencies, including network transmission times alongside raw computation durations whenever applicable. Incorporate profiling tools capable of identifying hotspots within application stacks. Modern IDEs integrate performance monitoring capabilities that highlight function call frequencies, helping pinpoint areas ripe for optimization. Don't overlook microbenchmarking needs too. Sometimes subtle differences arise only when examining very granular components isolated from broader context. These can reveal opportunities previously overlooked during higher-level analyses. Balancing optimization efforts across development stages. Prioritization plays a vital role in determining what gets optimized. Early-stage prototypes benefit most from clean, readable code emphasizing clarity rather than premature optimization efforts that complicate maintenance later. As product moves towards stabilization phases, gradually shifting emphasis towards performance tuning makes sense. This allows refining core workflows while maintaining sufficient flexibility required throughout iterative development cycle. Establish clear criteria defining when optimizations become necessary. Metrics should correlate closely with business objectives, whether aiming for reduced server costs via improved throughput or ensuring acceptable response times meeting SLA commitments. Implement gradual refactoring strategy rather than wholesale rewriting initiatives. Incremental changes maintain continuity, allowing continuous testing throughout transformation process, thereby minimizing disruption risks. Crafting efficient data structures. Selectively, data structure selection profoundly influences algorithmic efficiency. Choosing appropriate structures enables achieving optimal trade-offs between storage requirements and access speeds. For instance, linked lists excel in insertions/deletions but lag compared to arrays regarding random access speed. Hash tables provide fast lookups yet consume more memory relative to balanced binary search trees used for ordered collections requiring range queries. Context matters greatly. Applications involving frequent updates benefit more from tree-based solutions, whereas static datasets favor hashing mechanisms offering direct indexing advantages. Always evaluate alternatives against expected access patterns. If you anticipate mostly sequential traversals with occasional modifications, skip lists might present better compromise between insertion cost and navigation efficiency than traditional doubly linked nodes alone could offer. Concurrency and parallelism impacts. Leveraging concurrent execution opens new possibilities for improving algorithm efficiency. Through parallel processing. Carefully designed multi-threaded architectures enable dividing workloads among available cores, reducing overall completion time. However, concurrency introduces complexities related synchronization, overhead, and race conditions. Improperly managed threads risk producing incorrect results due to inconsistent state visibility across processors sharing same memory spaces. Parallelism extends this idea further by distributing tasks across different machines connected through networks. MapReduce paradigm exemplifies effective large-scale distributed computation, enabling massive data sets to be analyzed collectively, leveraging cloud infrastructure's elastic capacity. Optimizing for these paradigms necessitates architectural considerations distinct from single-threaded designs. Designing algorithms resilient to partial failures becomes paramount when deploying onto unreliable commodity clusters commonly found within public clouds today. Case study: optimizing database query patterns. One particularly impactful area involves database query optimization. Poorly structured SQL statements lead to full table scans consuming significant resources unnecessarily. Experienced DBAs employ normalization techniques to reduce redundancy, while denormalization helps optimize read-heavy operations, sacrificing some write efficiency gains for faster retrieval speeds. Finding right balance depends heavily upon specific application characteristics. Index creation follows similar principles. Strategic placement of indexes accelerates searches dramatically but consumes precious disk space and slows down update operations, requiring index maintenance activities during record inserts/updates/deletes. Modern ORMs abstract away much complexity associated with manual SQL writing. However, they also tend to generate suboptimal queries unless explicitly tuned by developers familiar with particular RDBMS engine behaviors and limitations. Performance pitfalls from common practices. Frequent mistakes occur when developers prioritize immediate coding convenience over long-term sustainability. Hard-coded values embedded deep inside logic layers limit adaptability, making future enhancements difficult without extensive rework efforts. Nested loops plague many beginner programmers, creating quadratic time complexities unintentionally. Replacing nested iteration schemes with set operations often yields substantial efficiency improvements. Overuse of recursion can introduce Stack Overflow vulnerabilities, besides generally being slower than equivalent iterative implementations for sufficiently large inputs. Always check base case conditions thoroughly before proceeding with recursive calls. Misunderstanding language-specific features leads others astray too. Using Python's list comprehensions wisely avoids unintended copies occurring during slicing operations, which waste both memory and processing power needlessly. Automation tools accelerate profiling tasks. Leverage automated profilers built into contemporary development ecosystems. Instruments like Visual VM for Java or Perf for Linux expose bottlenecks, visually highlighting functions taking disproportionate amount of execution time. Code coverage analyzers identify untested regions, exposing weaknesses in current test suites, possibly hiding undiscovered bugs waiting patiently beneath surface-level functionality checks currently passing verification steps. Static analysis tools detect problematic constructs early in development lifecycle, preventing introduction of bad habits becoming ingrained practices across teams, contributing consistently poor quality software outputs eventually. Continuous integration pipelines incorporate these checks, automatically enforcing minimum standards across commits, pushing forward, thus ensuring regressions never slip past final deployment stages unnoticed. Future trends influencing efficiency standards. Emerging technologies continuously reshape expectations surrounding algorithm efficiency. Quantum computing promises revolutionary leaps yet presents entirely novel paradigms challenging classical notions of time-space complexity trade-offs. Machine learning model inference times pose fresh constraints, requiring specialized accelerator hardware like TPUs/GPUs, otherwise rendering deployments economically unfeasible given current compute prices. Edge computing shifts responsibility back towards devices themselves, mandating lightweight algorithms suitable for resource-constrained environments, unlike centralized cloud offerings traditionally afforded luxury of powerful processing units. These developments compel ongoing education, keeping practitioners updated about evolving landscape, shaping tomorrow's definition of what constitutes efficient computing practices worthy of adoption now and going forward. Conclusion: mastering algorithm efficiency entails developing nuanced understanding, combining theoretical foundations with empirical validations derived from real measurements conducted systematically across various scenarios. By recognizing interplay between temporal and spatial factors alongside awareness about emerging trends reshaping industry norms, professionals equip themselves well enough to craft solutions performing reliably amid ever-changing technological landscapes ahead.